12.1 Lesson 2 Vector Valued Functions. Our objectives for today are 1. Represent the graph given by a rectangular equation with a vector valued function. And objectives 2 and 3 are you will be able to evaluate the limit of a vector valued function by using the definition of the limit of a vector valued function. So what do we mean by the limit of a vector valued function? And then objective 3, you'll be able to determine the intervals on which a vector valued function is continuous by using the definition of continuity of a vector valued function. So let's take a look at objective 1, representing the graph given by a rectangular equation with a vector valued function. We have example 3 from the textbook. Represent the parabola given by y is equal to x squared plus 1 by a vector valued function. To do this problem, we recognize that if we have a set of parametric equations, it's very easy to convert your set of parametric equations into a vector valued function. You would just take the parametric equation for x, and that would become the horizontal component of your vector valued function. And you would take the parametric equation for y, and that would become the vertical component of your vector valued function. And of course, as we learned yesterday, you can either write your vector valued function as a linear combination of the standard unit vectors I and j, or you can write it in component form as I'm showing you here. So the problem of representing the parabola given by y is equal to x squared plus 1 by a vector valued function is as simple as starting with the rectangular equation that's given and representing it with a set of parametric equations. And once we have that, it's very straightforward to write a vector valued function for the parabola given by y is equal to x squared plus 1. So how can we represent y is equal to x squared plus 1 with a set of parametric equations? You have many choices for how you can do that. But something that's really simple would be just to let x be equal to the parameter t. And if that's the case, then y would be equal to, since y is x squared plus 1, and we're letting x equal to the parameter t, then we will just have y is equal to t squared plus 1. So that would be our set of parametric equations. And now we can go from our set of parametric equations to a vector valued function. If we want to write it in component form, we will have t for the horizontal component, and we will have t squared plus 1 for the vertical component. You can also write the vector valued function as a linear combination of the standard unit vectors I and j. You'll have ti plus t squared plus 1 j. Our next objective is objective 2. You'll be able to evaluate the limit of a vector valued function by using the definition of the limit of a vector valued function. So we will start with the definition of the limit of a vector valued function. Definition of the limit of a vector valued function. We have one version for vector valued functions that represent plane curves, and another version for vector valued functions that represent space curves. But they are the same idea. For space curves, you just have one more component for the third dimension. So here's what we have. If you have a vector valued function r, such that r of t is f of t I plus g of t j, then the limit of the vector valued function as the parameter t approaches a is equal to the limit of the component function f of t as t approaches a multiplied by the standard unit vector I plus the limit of the component function g of t as the parameter t approaches a multiplied by the standard unit vector j, provided that the component functions f and g have limits as t approaches a. So a summary of what this states is, if you want to find the limit of a vector valued function, you have to find the limits of the component functions. So we say we find the limit of a vector valued function on a component by component basis. Let's go back to the vector valued function we found in example 3, and we'll use that to demonstrate the definition of the limit of a vector valued function. Suppose we want to take the limit of this vector valued function as the parameter t approaches 5. So we will have the limit of r of t as the parameter t approaches 5. And here's how we do it. We're going to take the limit of the horizontal component of the vector valued function r. So the horizontal component is t. So we take the limit of t as the parameter t approaches 5. And we multiply that by the standard unit vector I. And add to that the limit of the vertical component of the vector valued function. So we take the limit of t squared plus 1 as the parameter t approaches 5 and multiply that by the standard unit vector j. So what is the limit of t as t approaches 5? You may use direct substitution and you would get 5. Multiply that by the standard unit vector I. And add to that the limit of t squared plus 1 as t approaches 5. Again, use direct substitution. So 5 squared plus 1 is 26, and multiply that by the standard unit vector j. So the limit of a vector valued function as t approaches a particular value is a vector. And how do you find the limit of a vector valued function? We say we find it by a component by component basis. So we've taken a look at objective 2. You'll be able to evaluate the limit of a vector valued function by using the definition of the limit of a vector valued function. And now we will conclude our lesson by looking at objective 3. You will be able to determine the intervals on which a vector valued function is continuous by using the definition of continuity of a vector valued function. We begin by looking at the definition of continuity of a vector valued function. A vector valued function r is continuous at the point given by t is equal to a, the value of the parameter t is equal to a, if the limit of the vector valued function exists as the parameter t approaches a, and the limit of the vector valued function r as t approaches a is equal to the vector valued function evaluated at t is equal to a. A vector valued function r is continuous on an interval I if it is continuous at every point in the interval. And it says here from this definition, it follows that a vector valued function is continuous at a particular value of t if and only if each of its component functions is continuous at t is equal to a. So what we learned from this particular sentence here is that we find continuity, we analyze continuity of a vector valued function also on a component by component basis. Before we do an example, let's go back to the definition of continuity from Calculus AB so we can review continuity and then take a look at an example for using the definition of continuity of a vector valued function to do a problem. The problem that we do will ask us to determine the intervals on which the vector valued function is continuous. But before we do any of that, let's revisit the definition of continuity from Calculus AB. To understand the definition of continuity, we will start at the bottom of the screen by looking at 3 ways a function may not be continuous at a point C. So in the first case, at the very left, we have that this graph, if you look at the graph of f, there is a gap in the graph at x is equal to c. So when there is a gap, we don't have continuity because there is a gap. There is a discontinuity at x is equal to c. Why does that happen for the first case? Because the function f is not defined at x is equal to c. So when you look at the definition of continuity, it is stated in such a way so that none of these three things will happen. 1, 2, and 3. So if you look at the first condition in the definition of continuity, it states continuity at a point. A function f is continuous at a point c if the following three conditions are met. So the first condition is to make sure that we don't have a situation like what we have in the first example at the bottom of the screen. We don't want to have a gap in our graph, so we have to make sure that our function is defined at x is equal to c for it to be continuous at x is equal to c. Now look at the second situation. Is the function defined? Yes. How do we know that? Because you can see a filled in circle at x is equal to c for the top branch of the graph of f. However, here's what's going on with the second situation. If you analyze the limit of the function as x approaches c, you will see that the limit of the function as x approaches c from the left of c exists. So let's maybe say this is 2 here, and maybe this is 4 here. So in my example, the limit of f of x as x approaches c from the left would be 2. The limit of f of x as x approaches c from the right side of c would be 4. And because the left-sided and the right-sided limits are not equal to each other, the two-sided limit, in other words, the limit of f of x as x approaches c from either side, does not exist. We don't want that to happen because if that happens, we would have what's called a step discontinuity or a non-removable discontinuity. So to make sure that doesn't happen, we're going to require that the limit of the function as x approaches c must exist. And what about the third situation, number 3 at the bottom of the screen on the right side? Well, the function is defined at x is equal to c because you can see this filled in circle as a part of our graph. And the limit of the function as x approaches c does exist. So let's say that this is 2 here. So then we can see that the limit of f of x, as x approaches c from the left or the right is equal to 2. So the two-sided limit exists and it is equal to 2. So in this problem, we have that the function is defined at c, and again maybe this is 4 here. So we will have that f of c is defined and it is equal to 4 in my example. The limit of the function as x approaches c exists, it is equal to 2. But you can see from the graph that we have a discontinuity at c because we still have that gap. So how do we make sure that doesn't happen? So what we can do is we can require that the value of the function at x is equal to c has to be the same as the limit of the function at x is equal to c. In other words, basically make sure that this point will be filling in the gap. So we want to make that be the case, so we require that the limit of f of x as x approaches c must be equal to f of c. And in fact, this particular condition by itself implies the other two conditions. Because if you're saying the limit of f of x as x approaches c, you're assuming that that limit exists. So the left side of the third condition is implying the second condition is equal to f of c. So the right side of the third condition is implying the first condition. So sometimes we just state the definition of continuity by just having this because it includes the other two conditions implicitly. Now, how do you define continuity on an open interval? A function f is continuous on an open interval from a to b if it is continuous at every single point in the interval. A function that is continuous on the entire real line is everywhere continuous. So now let's compare the definition of continuity from calculus AB to the definition of continuity for a vector-valued function. When we make the comparison, the observation you should make is the following. Look at the definition of continuity of a vector-valued function. A vector-valued function r is continuous at the point given by t is equal to a if the limit of the vector-valued function exists as t approaches a, and that limit is equal to the value of the vector-valued function evaluated at a. So when you look at this requirement, it is like the third requirement from the definition of continuity. And as I said a minute ago, the third requirement in the definition of continuity implies the other two requirements in the definition of continuity. So basically, what we have is the same thing for definition of continuity of a vector-valued function. You would find the limit of the vector-valued function as t approaches a, make sure the limit exists. You would evaluate the vector-valued function at t is equal to a, make sure it is defined, and then you would make sure that the two are equal to each other. A vector-valued function r is continuous on an interval I if it is continuous at every point in the interval. And the important point that we want to make about using this definition is a vector-valued function is continuous at a point t is equal to a if and only if each of its component functions is continuous at t is equal to a. And of course, each component function of a vector-valued function is a real-valued function. So to determine the continuity of a real-valued function, you will be using what we just went over, the definition of continuity that we learned about in calculus AB. And this is actually something that you will see as we continue with our study, the idea of doing things on a component-by-component basis for vector-valued functions. In the next section, we will be finding derivatives of vector-valued functions, and how will we do that? On a component-by-component basis. We will also be finding definite integrals of vector-valued functions, and how will we do that? On a component-by-component basis. So let's take a look at an example for continuity of a vector-valued function. So now we will look at objective 3. We will look at an example for objective 3. So here we have number 75, determine the intervals on which the vector-valued function is continuous. And we have r of t is equal to ti plus 1 over tj. When we look at the definition of continuity of a vector-valued function, we see that we've got to make sure that the limit of the vector-valued function as t approaches a particular value a is equal to the vector-valued function evaluated at a. The problem is asking, determine the values of t for which the vector-valued function will be continuous. A vector-valued function r is continuous on an interval if it is continuous at every point in the interval. It would be easier for us to think, for what values of t will this vector-valued function not be continuous? And then it must be continuous for all other values of t. And as we learned earlier, we're going to do this on a component-by-component basis. A vector-valued function is continuous at t is equal to a if and only if each of its component functions is continuous at t is equal to a. So what we're writing here is the limit of the vector-valued function r of t as t approaches a. and that is equal to, from the definition of the limit of a vector-valued function that we had learned earlier. We do this on a component-by-component basis. So we take the limit of the horizontal component of the vector-valued function as t approaches a, multiply that by the standard unit vector I. We take the limit of the vertical component of the vector-valued function as t approaches a, and multiply that by the standard unit vector j. So let's go ahead and find each limit by using direct substitution. So for the horizontal component, we just have ai, and for the vertical component, we just have 1 over aj. Now, from the definition of continuity, we also have to consider the vector-valued function r evaluated at a. So we will have r of a. And again, all you do is you just substitute the value a for the parameter t in each of the component functions. So you have ai plus 1 over aj. So when you compare the two, they are equal, but is there a value of a that will give us a problem? The answer is yes. When a is 0, the vertical component function will not be defined because you cannot divide by 0. But for all other values of a, we don't have a problem, and we will in fact have that the limit of the vector-valued function r of t as t approaches a will be equal to r of a for all real numbers a that are in the domain of the vector-valued function. So what is the one value of a that is not in the domain of the vector-valued function? A is equal to 0, because that would cause division by 0 in the vertical component of the vector-valued function, making the vector-valued function undefined at t is equal to a. And of course, when you and that violates one of the requirements for continuity of a function. It has to be defined at t is equal to a for it to be continuous at t is equal to a, whether you're talking about a real valued function or a vector valued function. So to answer our question, we will go ahead and make a note about the domain. The vector valued function is defined for all a except a is equal to 0. So the domain here is all real numbers except 0. You can write it like that, or you can write it using interval notation from negative infinity to 0, not including 0, union from 0 to infinity, not including 0. So determine the intervals on which the vector valued function is continuous. Since this particular requirement from the definition of continuity is satisfied for all real numbers a that are in the domain of the vector valued function, the intervals on which the vector valued function will be continuous are these intervals, the same as the domain. So this is our answer. The vector valued function is continuous on the interval from negative infinity to 0, not including 0, union from 0 to infinity, not including 0. Today we looked at these three objectives, and the main thing that you want to learn about working with vector valued functions, whether you're trying to find the limit or determine continuity or later differentiate or integrate vector valued functions, you have to do all of that on a component by component basis.